Hi, I'm Haesol. Today I will talk about the protein side chain positioning problem. We're going to use a splitting method called Peaceman-Rachford. And this is joint work with Forrest Barkowski, who is a professor at University of Waterloo, and also with Henry, who's been my supervisor for a few years. So I'll present the work in the following order. I'll first introduce what the protein side chain positioning problem is, and then formulate into a mathematical program, and move on to forming a relaxation to this problem, and show how we solve the problem using, I'm gonna present the algorithm to solve this relaxation, and close the talk with showing a very strong numerical result. Okay, so let's talk about what the protein side chain positioning problem is. So I'll use only one slide to talk about what a protein is. So a protein is essentially a collection of side chains of amino acids. So here, a chain is a sequence of amino acids, and we can really think of it as having a bracelet like this. And the black line, the black solid line at the back, can be thought of as like a string in a bracelet. And each bead in this bracelet is an amino acid. So in this particular chain, there are 4 amino acids. An amino acid is a building block of a protein, and it consists of carbon, hydrogen, and oxygen, and nitrogen in general. And this is a typical picture of an amino acid. So there is an atom called alpha carbon in the middle, and it has 2 groups of atoms attached to it. So one is amino group, and the other is carboxylic acid group. We all heard of the name amino acid. It's in fact coming from these 2 groups. So the word amino comes from this amino group, and acid comes from this name acid in the carboxylic acid group. But what we're going to focus on today is this object called side chain. So this is a group of atoms anchored to this alpha carbon. So let's talk about what the protein side chain positioning problem is. So the setup is the following. So we're given a collection of sets of candidates for each side chain of amino acid. So we go to previous slide. What we're given is many candidates that can be picked as a side chain for this particular amino acid. And what we're also given is a pairwise energy values between all candidates. So now let's look at this picture. So in this picture, this black solid line is a backbone of this protein, and this black square is an alpha carbon. And this whole thing that I am highlighting is an amino acid. And what we're given is these 3 candidates for this side chain of this particular amino acids. And similarly, we are given 4 candidates that can be chosen as a side chain of this particular amino acid. And what I mean by pairwise energy values, it means that when I look at this node and this node, there is an energy value coming between these 2 nodes. So it's like having edges in a graph. And these are weights on the graph edges. Okay, and what we're going to do is to pick exactly 1 candidate from each set. And we want to yield the minimum energy value. So what it means is we're given 3 candidates in this amino acid, and we're only allowed to pick one candidate from each set. And also we want to yield minimum energy value. This means when we pick this node and that node from each group, there is an energy value coming from this edge and this edge and this edge. So we want to minimize such sum of energy values. And also there's another energy value coming from picking certain conformation, meaning when I pick this node, there is an energy between this node and the backbone itself. And this applies to every node that we pick. So this sidechain positioning problem has many applications. It is one of the most important sub-problems of the protein structure prediction problem. And examples are ligand bindings and protein-to-protein docking. So in the rest of the talk, what we're going to do is to formulate this problem as a quadratic integer program and obtain an SDP relaxation and apply a technique called facial reduction, and then obtain a tighter relaxation, which is a doubly non-negative relaxation, and then solve this relaxation model using a splitting method called Peaceman-Rachford. Okay, so now let's see how we can formulate our sidechain positioning problem into a mathematical program. So in a more mathematical terminology, this is how I describe this problem. So we're given a collection of disjoint sets, which is curly VI, and the cardinality of each set is equal to MI. And when I sum all the nodes in this graph, it sums up to N0. And I'm going to call VI a rotamer set. And I'm going to call each element in a rotamer set a rotamer. So the goal here is to select exactly one rotamer from each rotamer set. And we also want to minimize the sum of the weights on the edges between chosen rotamers. So again, what that means is when I pick this node and that node and that node, there is an energy value, which is weight, that's coming by choosing those particular nodes. And also the energy between each chosen rotamer and the backbone, meaning I pick this one, there is energy coming from the interaction between this node and then the backbone. So this is the mathematical program. So the variable here is binary. So 0 here means that we are not picking a rotamer. 1 means that we are picking the rotamer. And this linear constraint is reflecting the restriction that we are only allowed to pick one rotamer from a rotamer set. And this quadratic objective is reflecting our job. So we want to minimize the pairwise energy values and also interaction between a rotamer and the backbone. Okay. And so we can use even more compact notation. So we can form this matrix E and represent the objective as X transpose EX. And we can also form this block diagonal matrix A and represent this linear constraint as a matrix vector product. So AX equal to E. And this E is all one's vector of length P. However, this sidechain positioning problem is an NPR problem. So what we do is we work with the SDP relaxation. Okay, so now let's see how we formulate a relaxation to this binary quadratic problem. So we're going to use SDP relaxation. And the first thing to do is to lift the variable. So we had this vector X that has N0 coordinates and they're binary. Then we form this vector of length N0 plus 1 and take an outer product and work with this rank 1 matrix. So now our variable is now no longer living in space of R0 coordinates. It's now symmetric matrices of order N0 plus 1. And because we changed our variable, we need to make some modifications to objective and then constraint. So for the objective, we form this block diagonal matrix. So we just put 1, 0 at the top left corner. And then what we get is our objective value. Objective function is now equal to the trace inner product of two symmetric matrices. And for the constraint, this AX equal to E is reflecting that one rotamer has to be chosen from each rotamer set. So next steps are quite elementary. So we just pre-multiply this matrix and subtract x from the both side, and multiply this row vector both side and take trace. And what I want to emphasize is the second last line. This circle is a Hadamard product. So we are taking an element-wise product of two matrices. And what we can also show here is that this part, A transpose A minus the identity, is in fact a 0-1 matrix. So what it does is that whenever we have a non-zero entry in this matrix, it's setting the corresponding matrix as corresponding entry in this XX transpose to equal to 0. So that means, well, I'm going to represent this constraint as a gangster constraint. So what it does is that it's setting all the elements in this index set J to be equal to 0. This is easier to understand using a picture. So this is a y sub x. And by the structure of A, what we can have is this block structure in the matrix A. So whenever we have this block diagonal matrix, and we see this off-diag element, we're always setting those to be 0. And similarly, in this 2x2 block, whenever we see off-diagonal elements in this block diagonal matrix, we're setting those to be 0. And similarly, it goes on. And for the top left corner, it's always 1. So this is coming from this entry at the top. So that's why we get a 1 here. So this matrix E00 is all zero matrix with the top left corner being 1. Okay, so in fact, the word gangster coming from this picture because it looks like we're shooting holes into the matrix. Okay, and I'm going to call these indices to be a gangster indices. Okay, so after lifting the variable, the second thing to do is to drop the rank 1 restriction on our variable y sub x. So this is a summary of what we've done so far. So we started with this binary quadratic problem, and then lifted a variable and then formed this equivalent minimization problem. But what we had to put is this rank 1 constraint on the variable. However, having a rank 1 constraint is really hard. It's not even convex. So what we do is to lift this restriction and work with this general positive semi-definite matrix as a variable instead. So the advantage we get from doing this relaxation is obviously the convexity. However, there is a price to pay, which is a potential loss in the optimal value. So we relax the problem, so we know our optimal value of the relaxation might not be the same as the optimal value of the problem that we first started with. Okay, so next I'm going to apply a tool called facial reduction. Well, Faye already talked about it, so it might be a little duplicate here. So first, the definition. So a convex cone F is called the face of the semi-definite cone. So when we pick 2 points and form an open line segment in the set F, if the endpoint of the closure of this line segment is in the set, this object is called a face. So one of the nicest property of the semi-definite cone is that it is facially reduced. This means that whenever we bring a face of a semi-definite cone, it always has this representation. So the intersection of the cone itself and a hyperplane intersecting is 0. This is what is going on just pictorially. So we can think of this slice as a positive semi-definite cone. And when we have a face that also it is sitting in the boundary, and we can always find this matrix Z, which is positive definite, so that it kept the orthogonal complement of this matrix Z captures this face of a semi-definite cone. And we can also form a same equivalent representation of this face as V times a smaller positive semi-definite cone times V transpose. And we're going to see this representation throughout this talk. Okay, so now let's apply the spatial reduction to our side chain positioning problem. So AX equal to E is reflecting the constraint where one rotamer has to be chosen from a rotamer set. Then by putting this make all one's vector to the right and left hand side, we get this inequality. And we pre-multiply a vector and multiply a matrix on the right hand side. Then what we get is that this trace inner product and the value is equal to 0. And we already seen this matrix before. So this matrix is from the lifting from the binary quadratic problem. And this second argument, which I'm going to call it as K, this is positive semi-definite matrix because this is a grand matrix. So when two positive semi-definite matrices yield an inner product that is equal to 0, what we can also show is that the product of those two is also equal to 0, not just the inner product. So what this gives us is that K is an exposing vector to our model. That means every feasible point is always stuck in the null space of K, where this K is an exposing vector. So this is what's going on in picture. So this is the positive semi-definite cone of the order n0 plus 1. And this red shaded region is a feasible set. So what this equality is telling us is that whenever we bring a point from this red set, we can always show that it's always stuck in the orthogonal complement of this matrix K. What this also means is that we don't need to consider the whole positive semi-definite matrices of the order n0 plus 1 to work with this model. It suffices to work with this slice of a positive semi-definite cone to represent the entire feasible point of the model. Okay, so let's apply this observation to the model. So what we do first is to find this matrix V, and I'm going to pick the V so that it has orthonormal columns, and also the range of V is equal to the null space of K, the exposing vector. And so that we have this feasible set always stuck in this positive the slice of a positive semi-definite cone. So it's V times a smaller positive semi-definite cone times V transpose. Okay, so this is the positive semi-definite relaxation. And what we do is we include this Y equal to VRV transpose to the model. Okay, so this is where I added. And this Y being positive semi-definite is now implied by R being positive semi-definite by this equation. So after applying this Y equal to VRV transpose to our model, what we get is a very nice environment for using a splitting scheme, because we have two variables and one variable is in this gangster set. So this is a convex set, and we know we have a good understanding of this constraint. And also for R, it is sitting in the positive semi-definite cone. And we also have good understanding of this cone. And also these two variables are linked by this linear equality. And what we also get is a Slater condition. So we can always find an R here that is positive definite holding this constraint. So before applying facial reduction, we do not have Slater point. It's really because of this equation and this operation. It's not just the problem of this side chain positioning problem, but STP relaxation in general loses later points if there is a linear constraint like this in the underlying combinatorial problem. So fixture reduction is really cool because, well, now we have a strictly feasible point. Okay, now let's form a tighter relaxation, which is doubly non-negative relaxation. So before completing our model, I will show a little extra properties of the model. So let's say Y and R is they form a feasible pair to our model. Then for R variable, we can always show that the trace of R is equal to P plus 1. So P here means it's the number of rotamer sets. And for the Y variable, we can show that each coordinate of Y is always between 0 or 1. This is because our original variable was binary, so it was 0 or 1. And when we lifted the matrix, lifted the variable to the matrix, it should still be sitting between 0 or 1. Okay, so now we define two sets. So the curly Y is the intersection of the gangster constraint and this polyhedral box dot constraint. And for the set R, I'm going to define it as the intersection of the positive semidefinite cone, and then trace of R being equal to P plus 1. So we complete our model now. So I just described what this set Y and R are. And this Y equal to VRV transpose is coming from facial reduction. So this is a model that I'm going to work throughout the rest of the talk. So before presenting the algorithm, there's another extra property that we can show. So in fact, some elements of the dual multiplier are in fact known. So this is how the theorem reads. So let R star and Y star be an optimal pair. And let's say that Z is a dual multiplier for this Y equal to VRV transpose constraint. And we define this set Z sub A, which I'm going to explain in a moment. Then we can show that there is a dual multiplier, optimal multiplier, lying in this set so that this triple solves the doubly non-negative relaxation. So let's look at this picture. So this set is a dual multiplier, and E hat is the data for the objective function. And what we are only going to see is this yellow shaded region. So when I sum this yellow shaded region of these two matrices, if Z is dual optimal, it always makes those entries to be 0. This just means when this entry was -1, the dual multiplier in that position has to be 1. Well, this is 3, then that corresponding entry in Z has to be -3. And what E hat is the data, so we all know the numbers sitting in this matrix. So what this projection operator also is doing is whenever we have this, we put some matrix here, then it's always setting this yellow shaded region entry to be the negative of the matrix E hat. And in fact, this subscript A is coming from this picture because this yellow shaded region looks like an arrow. So this A is coming from the word arrow. Okay, so now I'll present the algorithm to solve this model. So as I said at the beginning of the talk, we're going to use a splitting scheme called a Peaceman-Rachford. So what we do is we first form this function called augmented Lagrangian. So this is Lagrangian function plus this quadratic term with the penalty parameter beta. And we initialize just the iterates and some of this penalty parameter beta and gamma, which is sitting in the open interval 0 and 1. And what splitting scheme does is we focus one variable at a time. So our variable is obtained by minimizing the augmented Lagrangian with respect to R while fixing the other two variables Y and Z. And then we move on to the dual multiplier, which follows this update. And I'll explain this red ink, this operation in a moment. And then we move on to the Y variable. We do the similar thing. So minimize augmented Lagrangian while fixing the other two variables. And then move on to a similar dual type update. So this projection is doing is what I explained just before. So whenever we have this matrix here, so we hit this dual update, what we do is that it's setting the error positions of this part of the matrix to be the minus of the E hat that we saw earlier. So I bring this and automatically set those entries to be the negative of this data matrix E hat. And we can still show that it converges. Okay, so I'll now present the formulas for our algorithm. So in order to have a very successful splitting scheme, it is important to have efficient minimization steps right here and right here, because whenever we hit this line, we don't want to spend so much time to solve this minimization problem. So in our problem, this is not too bad. So for our update, again, this is a copy paste from the previous slide. So from this augmented Lagrangian, by adding and subtracting some constant, we can complete the square like this. And this third line is coming from the choice of V. So we chose V, the matrix V, to have orthonormal columns. So by cyclicity property of the trace inner product, we can isolate this variable R. Then what we get is this projection. So the most expensive operation is the eigenvalue decomposition. And that is the most expensive part of our algorithm. And for the Haesol problem, we do a similar thing. So we minimize augmented Lagrangian while fixing the other two variables. And similarly, we add and subtract some constants and to complete this square. And what we get is we are only looking at the complement of the gangster indices and project those indices to this box constraint. So whenever we have a negative value, we are setting that to be 0. And when there is a value that is greater than 1, we're setting to be 1. So in computer, this is really, really cheap. Okay, so what we also do in our algorithm is getting bounds to have a feeling of how good our relaxation was. And also the point of getting a relaxation is to have a good lower bound. And in order to get this lower bound, we're using Lagrangian dual. So we form this dual functional, and then the dual is maximizing this maximizing this dual functional. And this inequality is coming from picking any Z. So in our algorithm, we're picking Z to be the dual multiplier at the point of evaluation. And what we can do is we separate this Y variable and R variable and end up with the last line. So this first minimization part with respect to Y is very cheap to compute. And then the second part only requires one eigenvalue decomposition to obtain this maximum eigenvalue of this matrix. So this is cheap. For the upper bound, we're using a projection strategy. So let xprox to be the second through the last elements of the first column of the Y iterate, or the most dominant eigenvector of the Y iterate. then we project this x-approx to the feasible region of the binary quadratic problem that we started with. So this quadratic term is this quadratic objective is just describing the projection. Then what we can also show, because of the constraint, this QP is in fact an LP. And in order to get an upper bound, we don't even have to solve an LP. What we do in the code is we partition this vector x-approx, and each partition, we're just picking the smallest value in a partition. So what I just mean to say here is that it's very, very cheap. Okay, so for the rest of the talk, I'll present the numerical result. So this is how we obtain the data. So the energy values in the matrix E are computed by the Lennard-Jones potential formula. So what this formula does is it brings the Euclidean distance between a pair of candidates, so those rotamers, and some type of preprocessing was done, which is called dead end elimination. And what dead end elimination does is it reduces the cardinality of each rotamer set. Then after getting this data, what we typically observe is this very, very large elements in E hat. So in this picture, like here and there in a matrix E hat, we have a number that are this big. So this is not even the biggest in the data. We sometimes see a 16-digit integer, really, really large. So when I see these big numbers in the algorithm, what I would do is to maybe scale the data matrix E hat. However, this is not a good idea in our setting because the other entries, for example, here is relatively small, maybe 0.5, or here it is maybe 1. So when I scale these relatively small number with such a big number like 16-digit, what it does in computer's eyes is that it's gonna make those entries look like a 0. Okay, so it's like destroying the data and we end up getting a garbage after termination. However, this is not a problem for us at all because of the updates that we are making. So to recall that the only place that this bad data you had is showing up is this Y update. So this is just copy paste from the previous slide. But the only place I'm going to focus is this E hat. So think about just ijth entry of this matrix E hat. Okay, and because it's negative multiplied to this entry, it's gonna make that ijth entry to be extremely negative. And when we look at the ijth entry of this matrix and that matrix, it's still going to set the ijth entry of this summation to be extremely negative because this was really large. Okay, then what this projection does is that it's setting that negative entry to be 0. So what that means is that there is no way that this big entry is coming into our algorithm and destroy my iterate. So this is really my favorite part of this algorithm. Also, we can think of this having an implicit gangster constraint on these large elements of matrix E hat. So it is also very intuitive because we are minimizing an objective value. Then what we should be doing is trying not to pick these big entries because these are very positive, a big positive number in this data. Okay. Okay, so this is the numerical result that I obtained. So these data are coming from a data bank called Protein Data Bank. And this column contains the name of each protein. And this P is a number of rotamer sets, and N0 is a number of nodes. And this is lower and upper bounds. But what I want to focus on here is this relative gap. If you look at this number, in this column, it's essentially 0. this means that we solved the problem to optimality because the lower bound and upper bound met. And I emphasize here is that we solved the relaxation problem. This is not the original problem, and we solved this to optimality, means that we solved the original binary quadratic problem to optimality as well. So this is done with the relatively small set. So for the bigger sets of problem, it does the same thing. So P now is in 200s. So this is the number of amino acid in this protein. And then 0 again is a number of nodes in our graph. And again, this is lower and upper bounds. And for relative gap, this is really, really small, meaning we essentially solve the problem to optimality. I emphasize again, this is a relaxation, not the original problem. And the original problem was NP hard. And I am also reporting this chi angle. So for the people who are working in this problem can see the results. So what chi angle is essentially doing is it's comparing our solution to the real protein. And this ratio is talking about how great our solution was compared to the original protein. And so this chi1, 2 is the ratio between chi1 angle and chi2 angle, if somebody is interested. Okay. So this is the conclusion. So we applied a technique called facial reduction. And what we got is a natural splitting of variables, because after facial reduction, we got an equation y equal to v times r times v transpose. And this splitting of variable enabled us to engage constraints individually. So without splitting, what we had to consider is the maybe intersection of the semidefinite cone and the polyhedral constraint. So considering these two constraints at the same time is headache. So we were efficiently separated this hard to engage at the same time constraints to separately and made our lives a lot easier. And we also obtained a very strong numerical result. We solved the NPR problem essentially to optimality in a relaxation. Okay, these are some important references. So for this talk, I used this work, this paper of Peaceman-Rachford splitting method for the sidechain positioning problem. And you can grab this paper from arXiv. And if anyone is interested in facial reduction, there is this nice survey paper written by Henry here in the audience. And if somebody is interested in proteins and how we get the data, you can take a look at this textbook written by one of the co-authors of this work. And there's also very cool software packages to play around a protein. So you can download protein data from a protein data bank, and you can put it into this software. You can also download this software for free and then play around with it. So by using this software, you can in fact get a picture like this. So there are a lot of functions that you can play with. Okay, so that's all I want you to say. Thank you for listening.
Okay, thank you very much, Haesol. It's a very nice talk, and even though I know the material, still find it really quite amazing how well this works. So there's one question that came up in the chat.
Oh, I'm sorry, I didn't.
No, I think I replied, but it was just whether the word rotamer should have been rotation.
Ah, okay. Actually, we're on the perfect slide. I put this picture just in case it comes up. The rotamer is the word rotamer, in fact, is coming from rotation. So in this last picture, you can kind of see this is trying to like rotate here. I guess maybe I should explain what these are. So the black, this part is a backbone. And maybe I should write. So this is a backbone, maybe I think this is nitrogen. And this is an alpha carbon. Can we use this? This is an alpha carbon. Okay, so so what that also means that this whole thing is an amino acid, and this part is a side chain for this particular amino acid. So you can see that this part is rotating, so that's why the word rotamer is coming from. I'm not sure if I explained that well. If you need more clarification, please let me know.
Itamar, do you want to?
Yeah, well, there is the folding is not the rotation, but it's like a partial rotation. Okay, but there is a rotation which happens in the protein, if I understand well. I think the biologists like to show you this structured molecule and proteins, and they show it rotating, so you see the structure in detail, not just one shot. So for me, the protein folding is not directly related to the rotation. It's only partial rotation. Okay, it folds and unfolds. But
Okay.
But you have many rotations here in the picture, which helps me a lot to understand that parts of the structures are having almost their own private rotation. So it's like
you're absolutely right.
engine. It's like a molecular engine that there is lots of studies with electron microscope cryo that explain those machines. And there is somebody at Sick Kids who does this stuff by the name John Rubinstein. So it's nice to look at his work because it sheds more light in detail what's really happening. So that's why I give his reference here.
Oh, could you spell his name?
Jonathan, like Jon.
Okay.
Rubinstein, like the pianist, and and he's at Sick Kids, and he does it for many years, and beautiful work. So it could be useful. Actually, to talk to him, since you're doing some theoretical work that he may be very interested in. So who knows, maybe there is some collaboration here.
Great. Thank you so much for the reference. I will definitely take a look at his work.
You're very welcome, and thanks for your great talk.
Thank you. I guess I can talk about this picture. So
actually,
yes.
Excuse me, can I interrupt? A question: the quadratic probe and constraints.
Leo, we're having trouble hearing you.
I'm off.
Maybe your connection is bad, Leo. Let me type.
Well, yeah, well, while he gets back, maybe I can explain this picture just a little bit. So this picture is coming from the software Chimera. So this software here. So this is the same protein, but I'm just trying to show how strong this visualization tool is. So this is one protein with all the surface because, well, each atom has a volume, right? So this forms, so it's like a surface. And this picture is only describing a backbone of this protein. So if you get rid of this like volume, this is just like a skeleton. And so this is again not the same protein, but different picture. So you can all see these spikes right? So these are all side chain of this protein. And so there is maybe alpha carbon here. So there's an alpha carbon, and this thing here is attached to this alpha carbon as a side chain. And this side chain gives the identity of this particular amino acid. So you can see how many side chains there are in this protein.
Haesol, can I ask a question?
Yes.
Yeah. So you mentioned that the SDP relaxation gives the optimal solution of the original problem. Is that correct?
Yeah, you can see. Yeah, you can see the
Right.
upper bound is obtained by having a feasible point of the binary quadratic problem. And this LBD is coming from the relaxation. So
Right.
this is true lower bound, and this is true upper bound to the binary quadratic problem.
Right.
And
So
I'm also working on explaining why we get such good relative gap.
yeah, it's really amazing that it's always used the optimal solution for the original problem.
Yes, it's crazy. So yeah, this is what I am working on, and I have some idea on how to maybe explain this. So maybe it's something to do with the data, like having huge entries in the matrix E hat. Also, one of the things that we get from the data is coming from this pre-processing. So what we do in this pre-processing is it's easier to see in this picture. So what this is too little. So suppose that there are like 30 candidates in this set and 43 candidates here. So after the pre-processing called data elimination, we reduce the cardinality of this set. Okay, and sometimes we get a set that has only one candidate in a set.
Mm-hmm.
Maybe it has something to do with it. So, well, you also work in quadratic assignment problem. So it's almost having the n by n block, right? Every block is same in QAP problem, right? But in this problem, this n by n sometimes becomes 1. This is 3. But we actually observe this one not too rare. So I think it has something to do with that as well.
Right.
Yeah, so there was some comment from Leo, because Leo's connection is bad. He was mentioning that there was some efficient branch and bound algorithm for quadratic over the simplex. But I don't think we have the simplex here, because as your picture shows, there are many assignment constraints. There's an assignment constraint for each set. So I'm not sure. I'm sorry that Leo can't reply. We can say anything we want about him, and he is held back by his typing speed.
Hello, Henry.
Hello, Leo.
Chat.
Sorry, you're still cutting in and out.
So he thinks that branch and bound can be adapted for a quadratic, so indefinite quadratic objective over, well, I don't know.
Oh yes, one of the things I didn't mention is that this matrix E is indefinite. Forgot to mention that. Very indefinite.
So he claims indefinite is fine. But Leo XE equals E is half of the QAP. So the other half, of course, is X transpose E equals E. So half works and double doesn't. So RLT for QAP, I guess, is a similar situation.
What's our RLT?
It's almost equivalent to SDP relaxation. It's the Adams-Shirali form, but it's no, okay. So RLT essentially
Isn't RLT somehow related to the non-negativity constraints?
yeah, it includes non-negativity as well as, yeah, the SDP just,
They're polyhedral constraints. They're
yeah, you
a way to
multiply.
linearize quadratic terms, but with polyhedral constraints.
So,
So you multiply non-negativity by a scalar as well.
Can you hear me now?
Yeah,
Oh, I'm just.
is that you, Leo?
Yes, it is me.
Okay, go ahead.
I'm
Take
on
over.
me.
Yes, we can hear you.
Good, good. So, anyway, worth a try before entering a branch to just formulate a small organs instance and generate constraints with the integer, see how it fares, something like this.
Sorry, you were cutting
See-
in and out, so couldn't catch all
cutting-
you're saying.
Cutting in and out.
Damn.
Did you know that decreasing noise in a modem is an EDM problem? Your modem has not solved the EDM problem very well. But I believe RLT. So Nathan, RLT should work if the SDP works well. The RLT may work well as also. But I think the magic here that's making things work is the splitting. Because the splitting, I don't know if Leo can still hear us. The splitting essentially means that the non-negativity is solved for free. So we're getting the non-negativity exactly, no relaxation on the non-negativity constraints. And it's very, very fast, essentially for free. Right, Haesol?
Yes, very, very cheap.
Yeah. So the non-negativity is just a rounding in the splitting. So the splitting is between the polyhedral, which includes the gangster and the non-negativity, and the projection on the SDP. So I don't see how the RLT is a relaxation, which includes the, am I right what you said, Nathan? Includes the non-negativity into the quadratic.
Oh yeah, that is true. I was thinking maybe I'm just confused, but oh, I think I remember now. I think it's the RLT is maybe related to triangle inequalities. Like if you switch from the 0, 1 variables, you would use RLT. But if you switch to the -1, 1 formulation, then you would get the triangle inequalities. So maybe that's what I was thinking.
I thought RLT. So for us, if we have AX equal B as a linear constraint, we can just go AX minus B norm squared and treat it as a quadratic and relax the quadratic.
Mm-hmm.
But suppose you had an inequality, AX greater or equal to B, a polyhedral.
Yeah.
Then you can still multiply on the left by a scalar, let's say X of 0, and on the right by a scalar X of 0. And the RLT is essentially relaxing those quadratics by adding a scalar to the polyhedral constraint.
I thought the was a way to represent the convex hull, the 0, 1 where the terms are quadratic. So you have quadratic terms in your model, and those terms come from 0, 1 variables. And if you look at the convex hull, then you can describe that polyhedron as using these RLT constraints.